We're going to do some basic review of parts of the atom. Hopefully a lot of this is going to be review stuff to you, but we're going to get into some more detailed stuff in terms of looking at atomic mass, mass number, the roles of neutrons and electrons and things like that that you probably haven't heard before. So a combination of a couple of things. So you might need to fast forward, but you know, there's some spots that you're definitely going to want to pause on. So again, today is about how are all atoms different from one another, and it's basically atomic structure stuff. So I know you've heard of the parts of the atom, protons, neutrons, and electrons, because you've made it through middle school. And so the question now becomes, why are atoms different? If all atoms are made of absolutely identical objects, what is it that makes elements different from each other? And then what makes reactions possible if they're all made of the same basic components to it? So again, some basic vocabulary here. Protons are the positive ones. Neutrons are neutral. They're not negative, they're neutral. And those two are located in the nucleus, the center of an atom. And then electrons are the ones that are outside. They're negatively charged, and they're the ones that are in what we now call the electron cloud. We call them energy levels or energy shells. There's a variety of different names for that. But the big idea is that you got protons and neutrons in the center, and then electrons around the outside. Again, nothing new here. So what is it that makes them different? One of the things that absolutely is still a mystery to us is how we can have atoms that are made of absolutely identical objects, protons, neutrons, electrons, and have them be so different from one another. One of the things that astounds me still is that every single proton in the universe is identical. You cannot tell one proton from carbon versus a proton from nitrogen. Same thing, electrons. Absolutely identical with each other, and neutrons are identical with each other. There's no difference between the particles themselves. What's different is something to do with how those particles are arranged that gives the elements as we know them their unique properties and their unique abilities to do different stuff in our world. So for example, carbon, the picture of that carbon over on the left, that's a piece of coal, basically pure carbon. Each atom of carbon in there, and there are trillions of atoms of carbon in there. Each atom of carbon in there has 6 protons. Super exciting, right? On the right, there's a picture of nitrogen. Now, it's a picture of liquid nitrogen turning to a gas. You know what nitrogen looks like in the air. But every atom of nitrogen has 7 protons in it. That's the only difference. Carbon's got 6 protons, nitrogen's got 7 protons. But carbon's a black solid, nitrogen's a gas that's a part of our air. Something is very different about those two atoms, and we're still not entirely sure, that gives them such different properties to it, and that's actually pretty amazing. So in order to kind of give that special status to these different atoms, we use the atomic number. Again, something that you've heard of before. Each atom has its own number. Every one is unique. And that atomic number tells you the number of protons, because it's the number of protons that really tell us which type of element is which. It's the 6 protons versus the 7 protons that makes it carbon and nitrogen. It has nothing to do with the neutrons or the electrons that are present. So atomic number, the ID number, gives you the number of protons that are present. So every single square on the periodic table has an atomic number to it, and you'll see it. Each periodic table looks a little different. This is a little different than the one that's in my classroom, so that's kind of why I threw it in here. But every square has got a little ID number in there somewhere. That atomic number is always a whole number. It's never a decimal place, and it's usually pretty prominent, like top and center, something along those lines on the periodic table, just depending on where it is. And if you look across the periodic table from left to right, they're always in order. So element number 51, which is antimony, is always followed by element number 52, which is tellurium. So that's just how it's arranged. They decided that quite a long time ago, that that was really the identifying characteristics that was important. So what are the other numbers then, right? If you've looked at a periodic table, each periodic table has at least 2. So what's the other one? That bottom number that's on there is called atomic mass. So atomic number is the number of protons. Atomic mass is exactly what it sounds like. How heavy is the atom? What we've got to be a little bit careful here is, and this is kind of the high school versus the middle school part of it, is that that number is an average. It's the average mass of that type of atom. And that mass comes from the two things that are in the nucleus, the protons and the neutrons. So if we take a look at carbon, we look at its average mass as 12.011. That means that the mass of the nucleus is roughly 12.011, or there's roughly 12 particles in there, 6 of which happen to be protons. So anyway, as they're arranged, when you're taking a look at a periodic table, if you're not sure which one's which, 2 easy ways to tell. The smaller number is always the atomic number. And the atomic number is the whole number. The atomic mass, the average, is going to be a decimal place kind of number because it's an average of a bunch of numbers all together. So it'll be the longer number. If it's radioactive, every once in a while you'll see that, students ask, it may have parentheses around it or be some other kind of unique number. But in general, the one that looks like an average is the average. Okay, so why do we have to have an average? Why can't we just have a number that's the same for every single one? It turns out that all atoms of an element are not identical. So not every carbon is exactly alike every other carbon. Some atoms of carbon are slightly heavier, some atoms of carbon are slightly lighter. So with this, these are called isotopes, and that maybe is a word you've heard of. Usually the word radioactive comes in front of it, radioactive isotopes. But isotopes are different versions of the same element. So it's still carbon, has to have 6 protons in every atom, but it has a slightly heavier or lighter mass. And if we're talking about the nucleus, which is what we're referring to here, we've got to be talking about neutrons. And the difference between isotopes is the number of neutrons they have, either a few more or a few less than we would kind of predict, I guess, to begin with. So this diagram that's on here shows 2 different isotopes of carbon. On the left there's carbon-12, and on the right there's carbon-14. And those numbers that we give after is what we call a mass number, and I'll talk about that more in a second. But that identifies the different weight of that particular type of carbon. So carbon-12 is by far the most common. That's this one that's 98.9% of all carbon in the universe is typical carbon-12. And carbon-12 means it's got 12 things in the nucleus, 6 protons because it's carbon and 6 neutrons. On the right, the other version of it, carbon-14, it's very rare in the universe. That's less than 0.1% in the universe. Is carbon-14 happens to be radioactive too, so that's probably a good thing. But that means its carbon-14 has 14 things in its nucleus. 6 of those things still have to be protons because it's carbon, but the remainder of those then has to be neutrons. And there's actually 8 neutrons in carbon-14, just a little bit heavier. So again, that gives you an idea of those 2 different isotopes of carbon. So let's take a look at another example of this to kind of bring this number home. So these are called mass numbers, these different isotopes. So this is lithium now instead of carbon. I used a different element. So lithium is atomic number 3, and you'll see that in each square that's on the screen. And there's 3 different isotopes here. There's lithium-6, lithium-7, and lithium-8. So lithium-8 is the heaviest. Lithium-6, is the lightest between them. And again, the only difference between these is not the number of protons. Protons has to be 3 every time. That's the atomic number. It's the number of neutrons that are in there. So lithium-6, the lightest one, has 3 protons and 3 neutrons to give you a total of 6 things in the nucleus. Lithium-7 would have 4 neutrons for a total of 7 total items in there. And then lithium-8 has 3 protons and it must have 5 neutrons to get that total mass in there. So what is it about neutrons? Neutrons are kind of weird. They don't have any charge. And so some people it took a long time to figure out what they did. What we now understand a little bit about them is that neutrons give some stability to the nucleus. I'm sure you've heard the phrase opposites attract. Well, the other side of that coin is that like charges repel. And so it's kind of weird actually that protons want to be in the nucleus together. Every proton's positively charged. So why would a bunch of positively charged things want to be stuck together in an incredibly small space? So the neutrons themselves, that neutral kind of space, it provides like a filler almost. It gives a little bit of a gap between the protons so they don't just want to fly apart from one another. But if you have too many of them as well, then there's almost too much space and it wants to fall apart, and that actually can make them radioactive, or that's what we would call radioactivity in unstable atoms. So anyway, that's the role of neutrons that are in there. Okay, so mass number and atomic mass, very similar ideas here. They both relate to the heaviness of an element. I'm using the element chlorine as a third example in this one. So mass number is specific. It's for a particular isotope, and it tells you the number of things in the nucleus of that isotope. So it's the number of protons plus the number of neutrons in that particular instance of chlorine, as opposed to atomic mass, which is an average of all the chlorines or all the atoms of that particular element together. So in this example, we've got 2 different isotopes of chlorine. Chlorine is atomic number 17, and the 2 isotopes of chlorine that we've got are chlorine-35 with a mass number of 35 and chlorine-37, which has a mass number of 37. So you can see in the blue square up on the top right, the average mass of chlorine is 35.45 something or other. So the mass numbers are specific. It's either chlorine-35 or chlorine-37. The average of all the chlorines in the world is 35.45. They're a slightly different idea. The table down at the bottom kind of gives you a little bit more details about it in terms of the number of protons is always 17. It's chlorine. The number of neutrons is different, right? Because that's what mass number and isotopes tell us. The number of neutrons in chlorine-35 is 18 versus 20 in chlorine-37. That's what makes it just a little bit heavier. Mass numbers are also given to you. Sort of by definition, chlorine-35 has a mass number of 35. That's what that number means. And then that last part, relative abundance, that chlorine-35 is a lot more common. About 75% of all the chlorine in the world is chlorine-35. Only 25% of it's chlorine-37. So if you average these numbers together, when you average together 35 and 37, the average sometimes people think is 36, right in the middle. But because that chlorine-35 is so much more common, the average kind of gets drug over towards that side. And if you take a look, that's why the average mass of chlorine is about 35.5. It's not right in between the two mass numbers. It's kind of drug over to the side. We'll do an example of that in class to give you a little more details. All right, enough with neutrons and mass numbers. Let's talk about electrons for a minute. Actually, electrons are the most exciting of all of these things because it turns out chemistry is actually really all about electrons. It's really what makes chemistry go. So with them, you probably learned back in middle school that the number of electrons and the number of protons is the same. And that's kind of true. It's sort of a lie, but it's kind of true. Middle school true, not high school true. The reason why is when we're talking about atoms, atoms are electrically neutral. So if you've got 5 protons, 5 positive charges, you have to have 5 negative charges to make that whole atom work out in a neutral sense. So again, for atoms, that's going to be a true statement. Protons will equal electrons. But as soon as chemistry starts happening and you're gaining or losing electrons, those charges start to change and they're no longer equal to one another. And this is what we start to talk about when we're talking about chemistry of ions. And ions are simply atoms that have a charge. They've either gained or lost some electrons, 1, 2, or 3, could be up to 5, I guess. Be really weird. But it's possible to have a couple, usually 1, 2, or 3. And that's going to give them this charge, which will allow some chemistry to actually happen. So a couple of definition words here. Cations are positively charged ions. If you like cats, that should help you remember that. And that's when atoms lose electrons. Anions are negatively charged ions, and that's when atoms have gained electrons. So it's kind of a weird backwards idea. Again, losing electrons makes it a cation, gaining electrons makes it an anion. And again, it's because the number of protons don't change. So if I have 5 protons, I started with 5 electrons and I gain 1, now I have 6 electrons. It's going to give you a -1 charge overall, 5 plus and 6 minus. Let's work on this in the next one here. So what does this actually look like? How do we figure out ion charges? So let's take a look at calcium ion, which is calcium with a 2+ charge. Don't worry about knowing what an ion charge would be. We'll learn about some patterns later on in this particular chapter. So how do I figure how many protons and electrons are in a calcium ion? So first of all, grab your periodic table. There it is. And you can see calcium right there. It's number 20. Actually happens to have an average mass of 40.08, but we're not using that here. So what does that tell us? Number 1, the atomic number is 20, therefore there's 20 protons. By definition, that number and protons have to be the same. That never changes. Number 2, the charge of this ion is 2+. So that tells us that there's got to be 2 more positive charges than there are negative charges in this particular ion. So if we're trying to do the math on this one, we've got 20 protons, 20 positive charges. There must be 18 negative charges to give that overall charge of +2. If you did it kind of backwards, and this is a second good guess, what if I did 20 protons and 22 electrons? If I did 20 plus charges and 22 negative charges, that would actually give me a charge of -2. So that's not what our question is looking for here, so that can't be the right answer. So again, big key here is always start with the number of protons. You can't change that, given to you by the atomic number, and then kind of figure out how many electrons does it have to be, kind of play with the numbers, guess and test if you need to give you the charge of that particular ion. All right, last one here. In terms of bringing all of this together, we can combine ions and isotopes just to see if you know what you're talking about. I know you don't, it's okay. But in terms of practicing on this one, so how would we write a full symbol for an isotope of an ion, oh my god, with 9 protons, 11 neutrons, 10 electrons? Okay, decode this. So it's going to be an ion, which means it's going to have a charge. It's an isotope, which just means I'm telling you the specific mass number of that particular isotope, so don't worry about that. And here on this middle thing with the E in the center, it's kind of that overall what these symbols kind of look like. You should have a mass number at the top. Sorry, the number sign got in a funny spot. Atomic number goes on the bottom. Charge goes on the right. So I'll give you an example of what this looks like, and we'll practice in class. So get your periodic table out. I started with that. Why did I pick fluorine? Because fluorine has 9 protons. Its atomic number is 9. And that's the key. If you can remember that piece, start there. So 9 protons means it has to be fluorine. It's got to be that particular one. Number 2, I can figure out its mass number. If If I know the protons and I know the neutrons, I add those up to get the mass number. It's the total of things present in there. So in this case, the mass number has to be the mass number of 20 because there's 9 protons in my example and 11 neutrons. Third thing, if it's an ion, I can now use the protons and the electrons to figure out what the ion charge is. Here I've got 9 positive charges and I've got 10 negative charges, 10 electrons. So if you add those two things together, we have to have a charge overall of -1, one more electron than protons. So here's what our final symbol is going to end up looking like. Again, mass number on the top, atomic number on the bottom, charge on the right, and that's what it looks like. So it's fluorine with a mass number of 20, top left, atomic number of 9, bottom left, and a charge of -1 on the top right. And that's what those ion symbols look like. That's a pretty complex example, so if you can do that, you're in really, really good shape. We'll practice this in class. Okay, overall summary, I know you've seen a table like this, but here's the big ideas of what you need to get in terms of protons, neutrons, electrons. You probably already know what the charges are. You probably already know where they are, whether they're in the nucleus or the electron cloud. By size here, I'm just talking about sort of relative size. We call the size of a proton and a neutron 1. An electron, just so you have an idea, is about 1,000 times smaller. They're tiny. They have basically no mass when compared to protons and neutrons. Importance and which number are kind of the new things for you, maybe. The importance would be protons are involved directly in the identity of an element. Neutrons are the ones that provide the stability to the nucleus and either help or prevent it from being radioactive, help the nucleus kind of hold its shape. And then the third one is reactivity for electrons. It's electrons, gaining, losing, or having them, that's going to cause chemical reactions to occur. On the right, just kind of a nice summary of which sort of numbers they're involved in, because a lot of these get really confusing. So proton is by definition the atomic number, but by kind of math-wise, I guess, it's also involved in the mass number. When you do neutrons and protons together give you the mass number. So that's why I kind of have that hint in there. And then electrons are involved in the ion charge. That's the number that they're involved with, and you have to compare those with the number of protons that are there. So this is a lightning fast overview to some of these things. I don't expect you to be able to do this perfectly, but here's some of the things that you should be able to do or maybe need to kind of think about. Basic stuff about protons, neutrons, electrons. Where are they? What size are they? What charge are they? You should be able to tell me a little bit more now about stability, about reactivity, and about identity, and which particular particle is associated with each one. You should be able to tell me a little bit about the difference between mass number and average atomic mass, like which one's on the periodic table, which one's a whole number, and which one's an average versus a count. And we'll practice some examples in class as well. You should be able to tell me the difference between an ion and an isotope versus a basic atom, like an ion has a charge versus an isotope has a particular mass number or maybe a different number of neutrons. And then you should also be able to, with some of those clues, be able to tell me the numbers of protons, neutrons, and electrons that are in a particular one. And potentially, even if you want to do something like this, write those symbols like on that very last slide of how to kind of represent which isotope it is or which ion it is. So there you go. Definitely some of these later parts get a little bit picky, so if you have any questions, ask me in class, and I'll see you the next time.